Hello everyone, my name is S.Hassaan, and I will be presenting my work on path-dependent controller and estimator synthesis with robustness to delayed and missing data, accepted in the HSCC 2021 conference. I will start off with the main motivation behind this research. Many cyber-physical systems nowadays involve distributed framework with a complex network of computers communicating via a shared channel. This can lead to communication delays among devices when more than one of those want to transmit data over the channel. For example, in a modern car, when hard brake is applied, the ABS system takes over the car communication channel, which may lead to other non-essential devices to delay their data transmission. In such scenarios, the main challenges rising are reliable state estimation as well as robust control in the presence of delayed or missing data. Previously, researchers have proposed various methods to tackle one of the two mentioned challenges. For estimation, researchers have used stochastic models for delays and proposed methodologies like Kalman filter-based designs and recomputation of past estimates when the delayed data does arrive. On the other hand, time-domain solutions of plant models are proposed to tackle the stabilization and control problem for systems with network-induced delays. But these works have focused on best average case performance rather than best worst case performance. Moreover, more recent research started to look into this area of proposed hybrid observers that achieve an estimator property called equalized performance with respect to estimation errors. A relaxed version of equalized performance called equalized recovery is also later introduced in the area of estimator design with missing data. They use a language-based model to characterize all possible missing data patterns. Apart from that, automata-based missing data patterns are also used for the analysis of controllability and observability of systems. But what if the delayed data, which these approaches have considered as lost, still holds some useful information that can be extracted once they arrive? So our work in this research focuses on equalized recovery setting in case of delayed data patterns. I will now introduce the terms of equalized performance and equalized recovery. Equalized performance was introduced as a property of state estimators that ensures that the estimation error stays within certain known bounds or desired bounds over all time periods. As, as can be seen in the figure here, the boxes representing estimation error bounds stays the same for all time steps and the trajectories stay within the boxes. In other words, the estimation error should lie within a desired invariant set. Now, when the plant output data is not available right away, the estimation error is expected to rise temporarily. For that scenario, equalized recovery is introduced as another property, which is a relaxation on equalized performance, allowing for an increase in intermediate estimation error bounds temporarily within a finite horizon before it gets back to the desired level. As seen in the figure here, the error boxes increase in the intermediate levels in the intermediate steps as estimation error guarantees are relaxed in the missing data scenario. Although these definitions were defined in the context of state estimators, they can be extended to control problems as well, where one of the trajectories is the desired trajectory or the equilibrium, like the red ones here, and the other trajectory is the true state trajectory, the same as the black ones here. Also note that throughout our work, we call the desired equalized recovery bounds as mu1, the ones that are at the end of the horizons, both ends, whereas the relaxed intermediate bounds are called mu2. With the definitions revisited, let's first define the system on which our work is done. We consider a discrete time, a fine time-varying system with process and measurement noise and time-stamped plant output. And we also consider communicated output separately, which is a set containing all model outputs received at time k, be it the delayed data from previous time steps or the on-time data from the current time step. The process or measurement noise bounds are generalized to be defined by the respective known polyhedral sets. For the delayed data model, we consider a set of allowable delayed and missing data patterns of fixed length of horizon t, calling the set a language, and each member is termed as a word, like each row in this illustrative example is a word. Each word consists of a sequence of values, like the column in this example, where each value represents the number of steps the data at that point is expected to be delayed by. For example, in this scenario, uh, and the blue color indicates that the data is on time at that particular step, whereas a yellow color indicates that the delay and the data at this point generated by the plant is going to be delayed by two time steps when it reaches the controller or the estimator. So if this value is greater than the remaining steps of the fixed horizon, that data can be considered as missing. If one knows the expected delay or missing data patterns, this language can be populated using that data, just as it's done here in this example. That if we know that our delay pattern is going to be any of these four patterns and only these four patterns, we just use these to form a language. But on the other hand, if that is not known, but a maximum delay possible is known, we can construct a language using every possible combination of delayed and missing data. This type of model can be interpreted as occurring periodically with a period of t following one of the words in each period. For this example, the language set can be represented as here. Now, before diving into the design, let's just define a transformed system using the model defined previously, which takes the different forms based on plant being targeted. If it's an estimator design problem, an estimator with an injection term is used, and the transformed trajectories and matrices defined above take the form of an estimation error system. If a control problem is being targeted, the plant model is essentially the transformed system. If it's a tracking control problem, the transform system incorporates tracking error. And now throughout this presentation, where all the mentions of state, input, output, etc., will imply these transform parameters. Moving on, the problem focus in this research can then be defined as follows. Given the transform dynamics, we'll relate data model as a fixed length language L, a desired equalized recovery level mu1, a recovery horizon t, and the initial state to be within a known polyhedral set. The goal is to design an optimal feedback law that achieves equalized recovery conditions on the transformed states over the horizon, while minimizing the cost associated with the intermediate error bounds. Here is a figure showcasing what the values mu1 and mu2 we are treating as in our research. Another problem that is considered is that given the delayed data model defined by a language L, the goal is to design a word observer, which is a tool that can estimate potential delayed data patterns from our language, given language L, that are compatible with observed patterns at each step k at runtime. As an example of what this problem is trying to focus on, let's consider this language with 5 words, which states that at first step, the data will always be on time, whereas data at one of the second or the third can experience a delay of either one or two time steps. Now at runtime, in the first step, suppose I receive the data which is expected because all the words in L convey that message. So at runtime, any of these 5 words could be what the model is experiencing within that horizon. So that is what we want the word observer to also point out. In the second step, if I receive data from the model, the word observer can then cross out the 2 words which indicated that the data can be delayed by one or two time steps, because this is not the system is experiencing that we know from the current history of data. If I had no data, the word observer would have only kept the grayed out words and then eliminated all the other words as those that are not possible as being followed in this current horizon. Now, on the third step, if I do not receive the data, I expect the word observer to tell that either of these two is what the system is experiencing. This way, a word observer can help detect data patterns, which can be useful for in fault or attack detection involving delayed data or losses. Note here that even though the end of the horizon is reached, the word observer still has multiple words detected as potential patterns. This is because of the definition of our language, where in the last step, because the data is delayed, doesn't matter if it is delayed by one step or two step, it is considered as missing. This is an important detection that shows that we expect the word observer to map the observed data pattern to many words. Moreover, the advantage of the word observer is when specific data patterns are expected are known and not constructed based on every possible combination. To solve problem 1, we first convert the given delayed data language into a reduced event-based language denoted as LE prime, which is a detailed binary representation of the given language. For example, if the given language is like here, with 4 words, its equivalent reduced event-based language is shown here. Let's take the last word. This word contains the pattern that the data at first step is delayed by one step. So the first value in its binary representation called an event is 0, indicating that the data at first step is not received in the first step. Afterwards, the whole pattern indicates and the whole pattern here indicates that the data at the second step is delayed by 1 too. That means that at the second time step, the delayed data from the first time step will be available, hence this 1 here, whereas the data from the second time step will not be available, hence this second value being binary value being 0. So note that that each event contains history of all available data at that particular step. For example, for this second word, where we do have received our data at the first time step on time, its corresponding event-based word has a 1 represented in the second event too, because in the second time step within this horizon, we automatically have the data from the first time step available as well. This combination of events over time corresponding to each word in the given language forms an event sequence for the reduced event-based language. Moreover, each subsequence of events of each event sequence forms a prefix, and each word in LE prime corresponds to a word in the delayed data language given. Furthermore, LE prime can then be used to construct an event matrix, which is later going to be used to group indistinguishable patterns that have same prefixes till sometime step k. The details of constructing LE prime are omitted to keep the presentation within time limits and are in the paper for those interested in looking into it. Lastly, an observed path is formed by observing data patterns of the observed outputs till some step k, which will be a prefix of some event sequence in LE prime. Now, to design the fine feedback logs of the inputs for the transform dynamics presented earlier, we consider two commonly used parameterizations. First one is the output feedback log, which uses the transmitted output of the transformed system as the feedback to form a switched affine signal, where the gains f and g are to be designed that are to be dependent on observed path. The other parameterization uses output fair error feedback law, where a Lindberger-like observer is defined, like here, and then the error between the transmitted output and the estimated output from this observer is used to define the switched feedback law. In this case, the gains to be designed are L, nu, and M, which are also dependent on observed path. Note that in both cases, the switching arises around whether new output data gets transmitted or at each step or not. Note that equivalent non-switching feedback laws can be obtained for both parameterizations. For output feedback law, one can constrain specific entries of the gain f to 0 for each non-reported output at each step k. Similar approach applies for output error feedback law, which constrains L and M. The reason these gains are dependent on observed path is because at runtime, we only need to select gains corresponding to the potential words whose prefix matches the observed path. So in the design phase itself, we will have separate gains corresponding to each event sequence in the reduced event-based language. We then constrain them based on the distinguishability of event sequences, rising from their prefixes till some step k being the same. This results in the constraint sets that we can apply on stack gain tuples, where stack gains can be obtained by stacking the system feedback law and other relevant equations defined earlier from k is equals to 0 to k is equals to t. So that leads to the constraint of this form. Here the function bm seen here means principal block miner, which basically extracts gain matrices from step 0 to some steps I, where that is defined by the subscript of this bm. Further, as mentioned earlier, non-switched feedback laws can be obtained by switching those gains by setting those gains to 0, which corresponds to the entries where the data is not available. These constraint sets are defined as here. Now I will focus on output feedback law approach. As mentioned before, since our work considers a finite horizon problem, the transform dynamics and the closed loop trajectories can be stacked over all k from 0 to t to get the following formulations. Note that in this particular formulation, the design gains appear in inverse matrix forms, for example, here, here, and so on, which makes the problem non-linear. To overcome this problem, we use Q-parameterization, which recasts the above equations with the following convex counterparts. Solving for these parameters Q and R, the feedback gains parameters F and G can then be easily obtained. Now, for the output feedback problem, an assumption is made here that any data that is delayed, even if it is transmitted within the horizon, will be treated as missing. Note that this is a strong assumption that can lead to conservatism, but this assumption will help keep the design approach linear. Moreover, in this assumption, the event matrix of an event sequence mentioned earlier will replace all the actual events with zeros for any data that is delayed. Now, recasting of gains from G and F to R and Q and back is not going to affect the sparsity constraints due to delayed and missing data. Moreover, the indistinguishability constraint introduced earlier is also found to be invariant under the assumption. Now with the assumptions, the system matrices and design gains can be reformulated as shown here. Because of these reformulations, the delayed or missing data constraint that was setting some gains to be 0 becomes redundant and can be omitted. Furthermore, the equivalent indistinguishability constraint on the recasted design parameters Q and R takes this form. Then the design problem for the recast gains corresponding to the output feedback law takes the form of this optimization problem, which minimizes the equalized recovery intermediate levels, subject to the constraints related to equalized recovery, as well as the state equation constraint obtained earlier after stacking the dynamics and closed loop law, and the indistinguishability constraint. Note that this problem contains semi-infinite constraints in the form of for all conditions. This can be easily overcome by using robustification techniques from literature, which results in this robust optimization problem formulation. As mentioned earlier, this problem is designed to be linear in design variables. So linear solvers can easily solve the problem to get Q and R, which can then be used to obtain the feedback design parameters F and G for output feedback law, as covered earlier. Now, for output error feedback law, again, due to finite horizon problem under focus here, the dynamics and closed loop trajectories can be stacked to form the equations as shown here. Do note that in this formulation, design parameters are multiplying with one another, which introduces non-linearity in this equation here, in these equations here. For this formulation, the previous assumption is not applied. So this formulation leads to more general case of delayed data, which is able to be received within the horizon and can be processed. So the design problem can be directly formed as this optimization problem, involving constraints due to the definition of equalized recovery and the equality constraint on the stage and input trajectories obtained in the previous slide after stacking trajectories, as well as the indistinguishability and delayed missing data related constraints defined earlier. Again, for all constraints results in a semi-infinite formulation, which can be converted into a robust dual problem that is shown here. As mentioned before, this formulation involves design variables multiplying with each other, so this optimization problem is nonlinear. However, because it involves a lot of sparse matrices, off-the-shelf nonlinear solvers like IPOpt can be used without any problems. Moreover, the parameter S0 has been found in previous work to have no impact on optimality, so it can be set to 0 without any loss of optimality. Lastly, if the Lindberger gain L is fixed instead of setting it as a design variable, this robust problem will also become linear, so linear solvers like Gurobi can be used here. Comparing the two approaches proposed in our work, the advantage of output error feedback is that it can be used for a more general case of delayed data as well as missing data within a fixed time horizon where it does consider delayed data when it arrives, although this introduces nonlinearities. But the overall problem is sparse, so nonlinear solvers can be used here. On the other hand, the output feedback law-based design, although does not utilize delayed data to its full potential, its formulation is linear, so it can be solved far more quickly using developed solvers for linear programs like Gurobi or Cplex. Compared to other implementations from literature, the proposed approaches employ time-varying intermediate equalized recovery bounds, resulting in less conservative designs. While path-dependent design variables allow for adaptive implementation of the controller or estimator that, that adjusts to the observed delayed data patterns at runtime. Now, with problem 1 solved, let's focus on problem 2, where a word observer is to be designed. As the observed path maintained at runtime is a prefix of an event sequence, it can be mapped to a set of compatible words in L. Here, some terms are introduced that are used in the construction of word observer. For example, an observer event sequence consists of events, which is a binary representation of the history of all available data from both the past and present within the horizon. The binary value is 0 when data is delayed or missing, whereas the value of 1 represents that the data has been received already within the horizon. Then the problem of finding the compatible word or words is just a matter of inverse mapping observed path, then only keeping those mapped words that are also present in the given delayed data language. Based on when the data is obtained, each of the potential values for the observed word is evaluated using this case structure here. Note that in the first case in this structure, by selecting from a range of numbers, that implies the previous expectation that the mapping from observed path to words in language may be one to many. That holds. With solutions to both problems proposed, let's move to the first simulation example, which is a state estimation of a batch reactor process. With the parameters specified here, the simulation is run compared using both proposed estimator design approaches as well as an optimal Kalman filter-based optimal estimator. The results show the output error feedback giving the best guarantees and best results, whereas the output feedback results in lesser optimal result due to conservativeness because of discarding all the delayed data. as covered earlier. Kalman filter-based approach from literature, on the other hand, has much higher estimation errors, even in the last step. For the second example, the adaptive cruise control is considered with the same setup as another similar literature implementation with missing only data implementation. Because it does not involve any delayed data, both results from the approach reach to same estimation error guarantees. The difference in trajectories is purely due to different solvers, where IP-opt is used for long linear problem and Gurobi for linear counterparts. But overall, due to time-varying nature of the bounds, the intermediate guarantees from both proposed approaches, like here and here, are naturally better, or rather lesser, than the other implementation from the literature, which has higher guarantees even for later steps. For the last example, a simple lane keeping system is used to perform cracking control, using the center line of the road as the desired trajectory. In this example, the polyhedron sets for the states are taken as hexagonal shape. Here, the results are shown using output error feedback law, with two different delayed data patterns being realized at runtime to show the adaptive behavior of the controller. I will now conclude the presentation by highlighting the contributions from our research. Mainly, path-dependent design problems are proposed that can be used to design both a controller and an estimator, which achieves equalized recovery requirements for guaranteed worst-case performance, and which takes delayed data within a fixed time horizon into consideration. The implementation uses time-varying equalized recovery levels for less conservative designs, which can adapt to the observed data patterns at runtime. Moreover, a word observer is also proposed that can map the observed data patterns to a set of potential words from the given delayed data model. For future extensions of this design approach to nonlinear system will be looked into. Here are some references used in this work. And with that, I will end my presentation here. Thank you for your time.